Okay, in this lecture, we take a look at the electric potential due to a series of point charges. So for example, let's say that I have two charges. Here's a Q1, and here's a Q2. And then right here is some point in space, point P. We want to calculate the electric potential at point P, where we make the assumption that the potential at infinity is equal to 0. So we're going to assume that V infinity is equal to 0. Okay, now each of these charges is a different distance from point P. So for example, Q2 is a distance R2 from point P, Q1 is a distance R1 from point P. And then we begin this calculation by setting up the following basic expression. VB minus VA equals negative integral A to B E dot dl. Okay, now here on the left-hand side, point B is going to be V infinity, which is equal to 0, and point A is going to be point P here on the diagram. But we've got these two charges, Q1 and Q2, each at different distances from point P. So how do I deal with that then mathematically over here on the right-hand side of the expression in terms of my integral? Well, what we do is we write down the net electric field. That's ultimately what goes here into the expression. Think of the net electric field as the electric field due to charge number 1 plus the electric field due to charge number 2. So let's go ahead and split this up into two integrals. We'll now write it like this. So V at infinity minus V at point P equals then the following. Negative integral from R1 to infinity of E1 dr. Once again, I'm switching variables here. I'll write down the electric field as Q over 4 pi epsilon naught R squared in just a moment. And then minus from R2 to infinity of E2 dr. Once again, this is the net electric field. It's electric field number 1 plus electric field number 2. And now let's go ahead and fill in the terms. Okay, so V at infinity is 0 minus the potential at point P equals the following. Negative integral from R1 to infinity of Q1 over 4 pi epsilon naught and then R squared dr, where we integrate from R1 to infinity. Okay, then minus R2 to infinity, Q2 over 4 pi epsilon naught R squared dr, where we integrate from R2 to infinity, like so. Okay, now here on the lower board, negative potential at point P equals integral of negative 1 over R squared is positive 1 over R. From R1 to infinity. Integral of negative 1 over R squared is positive 1 over R. From R2 to infinity. Okay, plug infinity into each calculation first, you get 0, minus then what happens when R1 is plugged in and R2 is plugged in. So ultimately then the right-hand side of the expression ends up being the following. Like so. And now the negative signs cancel. When the negative signs cancel, the potential at point P is nothing more than the potential at point P due to each charge added together. This is a basic expression. If instead of having just two charges, let's say that you had a number of charges, what we would do is we would add these terms together. The Q over 4 pi epsilon naught R's, you would add them all together. We write that then in the following manner. The potential at point P due to a series of point charges is equal to the sum over those charges of Q sub I, 4 pi epsilon naught R sub I, like so. You just add up all the Q over 4 pi epsilon naught R's in order to get the potential at point P. Okay, let's immediately now use this expression here in a basic example. Okay, let me go ahead and do some erasing. Okay, now let me write our result here on the board to refer to. This expression here, and then we have the following problem. Copy it down into your notes. Okay, two identical point charges, little q, are fixed in space and they're a distance d apart. So let's immediately begin to draw a diagram in the following way. Okay, let's say that right here is a q, right here is a q, and the distance between them is d. Those q's are fixed in space. And then a charge capital Q is placed midway between the charges. The charge capital Q is now moved a distance x towards one of the charges. What is the change in capital Q's potential energy? So what we have here are 2 points that we have to worry about on the diagram. Okay, point number 1 we'll say is exactly halfway in between the 2 charges. We're going to find the potential there. And then we're going to move the capital Q a distance x towards one of the other charges. It doesn't matter which. So let's say that right here is point 2 on the diagram. This distance here is x. So what we need to do is we need to calculate the potential difference between these 2 points. Multiply that then by the capital Q, and this then gives us the change in potential energy. In other words, we're working with this portion of the expression. Change in potential energy per charge, in this case the capital Q, is equal to the potential difference. We have the initial point here and the final point here. So we're going to take the potential at point 2 and subtract from that the potential at point 1. So I need to calculate this and this using this expression and then multiply by the capital Q in order to obtain the change in potential energy. Once again, you just follow the math. Follow the math in these calculations, and that then ultimately tells us what has to happen. Okay? Okay, so let's go ahead and first of all find the potential at point P2. That's this value here. I'll do this off to the side. All right, so to do so, first of all, for this Q, we need this distance here. This distance here, you'll notice, is 1/2 d plus x. So then therefore, the potential at this point due to this charge is Q over 4 pi epsilon naught 1/2 d plus x. But then we have to add to it the value of the potential due to this charge here. Okay, this distance here on the diagram, you'll notice is 1/2 d minus the distance x. So the potential at point P2 due to this charge is Q over 4 pi epsilon naught. And then we have here this distance, 1/2 d minus x. So. Okay, and now we do the same sort of thing here for the potential at position 1. So the potential at position 1, okay, first of all, for this charge, that distance is just 1/2 d. So it's Q over 4 pi epsilon naught times 1/2 d. And then similarly for the other charge, which is also a distance of 1/2 d, Q over 4 pi epsilon naught times 1/2 d. And then if we wanted to, we can get a common denominator and add up the expressions and blah, 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 but just leaving it like that is perfectly fine. All right, so then therefore, we essentially end up with kind of a mess here when calculating the change in potential energy. So the change in potential energy is going to be capital Q and then multiplied by the following. First of all, VP2, which is this thing right here. Like so. Okay, and then minus VP1, so minus each term. Like so. And then if we wanted to simplify further, we could if we want to, but leaving it like that, quite frankly, is good enough. Okay, we'll take a look at one more point charge calculation in the next video.